Hello everybody, it's Tarun. Welcome to your third tutorial in the signal system and control course. In the last tutorial I talked to you about the elementary signals, and in this tutorial I will teach you about the continuous time and discrete time systems and the basic system properties. Okay, so what is a system? A system is actually a representation of physical processes, and it is a entity, or you can say a device, or something which transforms input signals into the output signals. Okay, so there can be more than one input signals and output signals for a single step, and continuous time system will take continuous time signal as its input and will produce continuous time signal as its output only, and discrete time system will take discrete time signal as an input and will produce discrete time signal as an output only. Okay, so there is a formal representation of input output relation which is used generally everywhere. So for continuous time we represent a system by this xt, then arrow to yt, and for discrete time xn to yn. Here okay, xt to it and xn to yn. Here xt is the input signal and its corresponding output is yt, and here xn is the input signal and its corresponding output is yn. And in some books you may find that this term is used for representing a system, where S operator is the system operator. Okay, so we can represent any system with the help of block diagrams, or say pictorially. So this is how we represent any system. Here is the input, and here is the system, and here is the output. Okay, so the input goes in, get processed in the system, and then output is being produced. Okay, so this is the pictorial representation of systems. So now I am going to tell you some examples of system. Well, there are some examples such as the quadratic system. In the quadratic system, if you pass xt as input, then your yt will become xt square, as you can see here. So if a system which is first order differential equation, it gets processed like this, that you input the signal xt, and after processing the signal you get this equation. Okay, where this is y dot t, which is dy over dt. And delay system, in delay system your system, the input signal which was at the original pay gets shifted by one value on the right side. Okay, it gets delayed by one value. And for a first order difference equation, like we talked about in the first order differential equation, this is the change in the signal when input xn is given to the first order difference equation. Okay, so you might be thinking that how is it possible that I give xt as input and get this equation after the processing inside the system, and same here for this equation. But don't worry about that, I'll teach you that in the next unit. Okay, it is there in the next unit under the title of block diagrams. So now let's move forward to the interconnection of systems. We can divide a complex system into small parts to easily understand it. So if a input is passed to system 1, then through system 2, and then we get the output. Okay, it is called series or cascade interconnection, and its example are communication channel and receiver, detector and decoder in communications. Okay, so if in cascade connection, if you replace system 1 by system 2, okay, if system 1 is replaced by system 2 and system 2 is replaced by system 1, then the output will be same. Okay, so it is one property of the series cascade connection. Now let's see parallel interconnection. This is the parallel interconnection in which a input is given to two systems at the same time, and then their summation is done to get the output. Okay, so the example of this is diversity transmission, which is transmitting the same signal over two antennas and receiving it with one antenna. Okay, the next type of interconnection is feedback interconnection. In the feedback interconnection, what we do, we pass the input to a system. Okay, and we take the input and pass it to another system, and then sum them or add them, and then get the final output. So the equations, the difference equation and the differential equations which we have talked about earlier, are examples of feedback interconnection. Okay, so the examples of feedback interconnection are closed loop frequency, phase timing synchronization in communication, and human motion control. Okay, so example just to your knowledge, they are not so important. Okay, but you need to remember all these block diagrams for different connections. You can be asked to create any connection with by asking that create a series interconnection of this system, or create a parallel interconnection of this system. Okay, any questions like this can be asked. So now let's move forward to the last topic in this unit, which is basic system properties. Okay, there are some mathematical formulations which the physical system always follows. Okay, such as if we replace the variable t by n, then the definitions for continuous time signals will become the definitions for discrete time systems. Okay, so now let's see the properties. First property is linearity. Okay. If x1 of t is going to y2 y1 of t, and x2 of t is producing output y2 of t, okay, then x1 of t plus x2 of t will produce the output y1 of t plus y2 of t. Okay, and this is called additivity in the linearity section. Second one is homogeneity. It says that if you multiply a scalar, okay, which is complex in nature, with a input signal, then your output will be multiplied with the same scalar. Okay, and this is the generalized way for this homogeneity equation. Okay, so here k equals to 1 to k, and you can see that it's just a general way of showing the homogeneity. Okay, non-linear systems are referred to as non-linear. So example, let's see, our system is yt equals to t x of t. Okay, so x1 of t will produce y1 of t, so y1 of t will equal to t x1 of t, and x2 of t will produce y2 of t, which will be equal to t x2 of t. So now let's check that x1 of t plus x2 of t, what will it produce? It should produce y1 of t plus y2 of t as output. Okay, so I am considering x3 of t as ax1 of t plus bx2 of t, and if I am taking this as input signal and passing it through the system, and I will get output t x3 of t. Okay, which will be t ax1 of t plus t bx2 of t, and here you can see that ax1 of t is y1 of t, sorry, t x1 of t is y1 of t, t x2 of t is y2 of t, so it is equal to a y1 of t plus b y2 of t, which shows that the system is linear. Okay, now let's see an example of non-linear system. The system is yn is equal to xn square, okay, which is a quadratic system. Now so in the checking of linearity, there are some steps which you need to follow. Okay, which is first, take one signal x1 of t and find out its corresponding output. Take second signal x2 of t, find out its corresponding output. Take third signal x3 of t in the form of ax1 of t plus bx2 of t, and then find the output corresponding to this signal x3 of t. Okay, and check that whether LHS and RHS are equal or not. If they are equal, then your signal is linear, system is linear. Now let's see for this. Now I have taken that x1 equals to x1 as the input, then y1 equals to x1n square. If I take x2 as input, then y2n is equal to x2n square. Okay, now I take x3n equal to x1 of n plus x2 of n. Here I have taken value of a and b equals to 1. So now y3n will be equals to x3n square, which will be equal to x1 square plus x2 square plus 2x1 x2, and you know that x1 square is y1n and x2 square is y2n. Okay, so you can write y3n equals to y1n plus y2n plus 2x1 x2n. Okay, which is not equals to y1n plus y2n. So you can see that the system is not linear. So there is third example, which is yt is equal to xt's conjugate. Okay, star means conjugate. Okay, okay, you have heard it in the complex numbers. So now let's see the second property, which is time invariance. Okay, this property tells that if a system is changing with the time. Okay, so if I change the system with respect to time, or if I delay it or advance the signal, then if the output does not vary according to the change in the input, then the system is time invariant. If it does change, then the system is time variant. Okay, so let's see an example. Okay, yt is equal to xt square. So to do it, okay, to check this, what you should do, take the signal x1 of t as say x1 of t equals to x of t minus t naught. Okay, and then find the output corresponding to x1t, and in this case the output y1t equals to x1 of t, x1t square, and if I consider this as my output, and then the equation will be x square t minus t naught. Okay, so if I have calculated y1 of t as x1 of t square, and if I replace x1 of t with x of t minus t naught, then it will be equal to y1 of t is equal to x of t minus t naught whole square. And if I replace t with t minus t naught in this equation, okay, then it will become y of t minus t naught is equal to x of t minus t naught whole square. Then you can see that y of t is equal to y1 of t, which shows that this system is time invariant. So this is the exercise for you to check for the second example. Okay, now let's see systems which have memory and which do not have memory. So a memoryless system, the output of memoryless system will depend only on the present value of the input signal. Okay, if the output signal of the system depends on past and future inputs, then the system is called memory system, or the system possessed to have a memory. So let's see example. Okay, for first of some memoryless systems. If phi of n equals to x of n for minus a to a, and minus a for less than minus a, and plus a for xn greater than a. Then you can see that if I put any value of xn between a minus a and a, then it will be yn will be equal to xn, and it has a constant value before minus a and constant value after a. So its output does not depend on the past and future inputs. So this system is memoryless. Second one is this amplifier y of t is equal to ax of t. Here you can see that if I put t is equal to 0, then I will get y of 0. If I put t is equal to 1, then I get y of 1. If I put t is equal to minus 1, then I will get y of minus 1. Okay, so you can see that the system does not depend on past and future inputs. So this system is memoryless. Now let's see system which have memory. First one is accumulator, second one is delay, and third one is capacitor. So let's first see accumulator. The accumulator system has this equation. Okay, and in here if I put a value of n equals to, let's say, 0, so y of 0 is equal to x of 0 plus y of minus 1. So now you can see that the y of minus 1 will not exist. So if I put n equals to 1, so y of 1 is equal to x of 0 plus x of 1 plus y of 0. So you can see that in this case the system is dependent on the past value of the input. So this system is having memory. And now let's see for delay. Okay, and in delay you can see that if I put t is equal to 0, so I'll get y of 0 is equal to x of minus t naught. So which is also an example of memoried system which depends on the past values. And this function, capacitor function, y of t is equal to 1 upon c integration minus infinity to t x of tau d tau. So this function also depends on the past values. As for calculating the value at 0th position, you need to calculate the integral from minus infinity to 0. Okay, so this is the example of memory system. So now let's see another property, which is invertibility and inverse systems. So what is invertibility and inverse systems? Say that if I pass any input through a system and I'll get some output, and if I pass output through another system, and then the output of that another system which I'll get will be equal to the input of the first system. Okay, so here you can see that this was my initial input and this was my first output. So if I pass this output through this system called the inverse system, and then I'll get Wt as my output, which is equals to x of t. So if a signal which follows this property is known to be invertible, and the system which allows the signal to process back to the original signal to perform invertibility is called as inverse system. Okay, so let's see an example. Amplifier, y of t is equal to ax of t, and the constraint is there that a should not be equals to 0. So the inverse system for the amplifier will be 1 upon a y of t. So when I pass the output y of t through this system, then I'll get if I pass the value of y of t in this system, so if I put y of t is equal to ax of t, then I'll get Wt is equal to x of t, which is the output after the inverse invertibility. So another example is accumulator, in which you can see that y of n equals to y of n minus 1 plus x of n. So the inverse system for this is y of n minus y of n minus 1. So if I put the value of y of n minus y of n minus 1, which is equals to x of n, so you can see that the system is invertible. So let's see some example of non-invertible systems also. So in the limiter function which we talked about earlier is an example of non-invertible system, because there is no function or system exists which can invert the output yn to go back to xn. and same goes for slicer. Okay, so now let's move forward to the next property, which is causality. And causal system is any system whose output depends only on the past and present values of the input. Okay, there is slight difference between memoryless system and causal systems, is that the memoryless system's output depends only on the present input, but the causal system's output depends on past and present input. So if x1 of t is equal to x2 of t for t less than equals to t naught, then y1 of t is equal to y2 of t for t less than equals to t naught. Okay, so let's see some example of causal system. That accumulator y of n equals to x of n plus y of n minus 1. So here you can see that if I put 0, then y of 0 equal to x of 0 plus y of minus 1. So you can see that the output of the system y of 0, y of n is dependent on the current input and the previous input. Okay, so now let's see example of non-causal system. Y of n equals to 1 upon 2n plus 1, then summation k is equal to minus n to n x of n minus k. So here you can see that if this was limited to minus n to 0, then I could have said that this averager function depends on past and present input only, but since it goes from minus n to n, then I can tell you that it depends on future input values also. Okay, so this is not a causal system, and causal systems or all memoryless systems are causal because the memoryless system depends on present value only, so it is a causal system. And causal systems are used in real time processing. Okay, so now let's move forward to the last property and the last topic in this unit, which is stability. Stability is checked by the Bibo conditions, which is bounded input, bounded output stability condition. So if your input is bounded, and bounded means it has some maxima for the signal, then your output signal is also bounded. Okay, and then the system will be stable. So if xt is less than equals to bx, which is less than infinity, it means that it is finite. So and your output signal is bounded also. Yt is less than equals to by, which is also finite, less than infinity. So the system will be stable. So let's see an example. Averager function y of n equal to 1 upon 2n plus 1 sigma minus k equal to minus n to n x of n minus k. So I have considered that xn mod xn is less than bx, and which implies that yn will be less than equals to by, which is equals to bx. So the system will be stable. And let's see an example for an unstable system, which is integrator. Okay, y of t equals to minus infinity to t x of tau d tau. So if I take bounded input xt equals to ut, then I'll get unbounded output yt equals to t. So you can see that I have bounded input, but the output is not bounded, so this system is not stable. Okay, so this was all from my side in this tutorial. Till now we have completed the unit 1, and in the next tutorial I will start with unit 2. But before you start watching the unit 2 tutorials, there is an assignment with this unit, so you should do the assignment with okay. I also provided the hints for the assignment, but I'll suggest that you do the assignment by yourself, because it will help you understand the concepts of this course better. So thank you guys for watching. I'll see you in the next tutorial.